So it turns out that psychology is wrong. There's this concept, they tell me, of Gestalt, and it means that you're more than the sum of your parts. I don't mean to hurt your feelings, but technically, physically speaking, you are less than the sum of your parts. What I mean by this is that, you know, that, well, what did they tell you? That mass is energy? Yeah, something like that. What I mean is, when, you know, nature hates change, right? You know, nature seeks to reduce energy. This is my last video. Sorry I'm throwing all this stuff at you. But what I'm saying is that nature seeks to reduce the energy of a system all the time. And lower energy actually means lower mass. So if I have, for instance, a proton here and another proton here, they could reduce their energy if they were in fact bound by the strong nuclear force. So the mass of one proton and the mass of one neutron, for instance, or the mass of a proton and a proton as I've drawn here, the masses of them separately is more than the mass of them in a nucleus. Like, let's take one of those and one of those and one of those and one of those. We got a neutron here and a neutron here, and we've got a proton here and a proton here. If I add up the masses of all of these things, it's significantly more than if I make myself a helium nucleus. So I'm gonna make you a graph, in fact, of the binding energy per nucleon, and that graph looks like this. Here's a good graph. We got an axis here, which is binding energy per nucleon. Okay, and then over here, we've got mass number. So as I'm talking about bigger and bigger elements, I'm going to be going this direction. What do we use for mass number? N, M, A, what? Oh, I think it's A. Okay, then, oh, what did we have? We had A plus something, N equals A, B, what? All right, you look that up, figure it out. Watch this. I've got these numbers. There's one important number here, which is the top, 8.8 MeV. That's millions of electron volts. And then if I go up here, what the heck? Okay, great. And then it jiggles around a little bit and ultimately peaks right there at 8.8 million electron volts, and then it gradually goes down. This process here is rather slow, so slow that if I call out the next data point that I can see here, this is an interesting number to me. This data point right here is actually at 7.5 MeV. Okay, and what I really mean is this is the energy that binds the nucleons, so this ought to be negative. This whole graph, it always pisses me off to see it like this, but the whole graph ought to be negative. So the safest, the most bound things are right here at the peak, and the things that are least bound, most able to escape, are over here and like way over here. Wow, 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 way able to escape. So it turns out that the very peak of this graph occurs at iron. And that's where the nucleus is absolutely the most stable. It has something to do with filling up shells. That's why we get this this 2 pattern here, and then it gets slightly less stable here at that peak. And this dot right here is actually hydrogen, but it's not regular hydrogen. It's got one proton, but it's got one neutron also. And then this guy right here is hydrogen with 2 neutrons. There's H right there. Wow, okay. And this is probably helium right here. And way down here, we're going to get uranium and plutonium and stuff. So this is really a fascinating graph. I want to try to understand why there's more binding energy at iron than there is in hydrogen. And that means divided by the number of nucleons. So this is like an efficiency kind of problem. The reason that you get a less strong bond here with hydrogen than you do, for instance, with helium, is because if I have just a proton and a neutron, then they're right next to each other, but if I could stack another one right here and another one right here, this would be a tighter system because these guys are closer, actually, than, like cumulatively, these guys are closer net than just having 2 of them this far apart. So because of the 3-dimensional antics, we can stack these guys here. So the closer we stack them, we emphasize this strong nuclear force, the force of attraction between these nucleons. But as I go to iron, they get more and more crowded, ultimately going here. The reason that it tapers off is We say that the nuclear force saturates. So the strong force saturates out here. Let me write that down. And by saturates, I mean that it doesn't get any bigger because this nucleus is so big, it's like, you know, hundreds of nucleons now. This proton over here might not feel, well, it doesn't. It doesn't feel the force of attraction from the strong force to this neutron over here. And in fact, what they're only going to do is they're only going to see their nearest neighbors. I'll say this region right here is attracting that particular proton, and this region right here is attracting that particular proton. So ultimately, we still get adding more nucleons in here. We're still going to get some electrostatic repulsion. There's a proton there. It doesn't like that one. So in fact, these guys are becoming less and less stable, and that's why ultimately this falls off and you don't get any stable elements over there. Okay, so that's a little bit funny, but where do I want to go next with that? Oh, right. In 1939, Hahn and Strassmann discovered that uranium could split into about half. This was kind of crazy, and it really changed World War II and, heck, a lot of the 20th century. So here we are. Hahn and Strassmann, 1939. They sound like Germans. Wow. Hahn and Strassmann discovered fission. And fission is not just electrons leaving a nucleus, or protons leaving a nucleus, or alpha particles leaving a nucleus, or neutrinos leaving a nucleus. Fission is a little bit different. Fission is taking uranium, in their case, and it was, well, I don't know, uranium-235 maybe? Maybe they started with uranium-235. What do we have down there, 92 or something? And then after a moment, it broke into two things, one probably going that way, and one probably going that way. And the way to get it, though, well, let's not talk about the way to get it yet. But I want to bring this graph back here. I want to get this graph, and you see, the thing is, uranium is not as tightly bound as iron. So if we broke uranium into about half, we'd be going to maybe right here or something. It turns out that that level is going to give us 8.5 or something MeV per nucleon. All right, and if we're at 8.5, or maybe it's not even that bad. Maybe it's only 8.3. So what we're going to do is we're going to have a more efficient binding if we can split these guys apart. So the cool thing is, oh, if you're made of very heavy things, you might actually be more than the sum of your parts. So uranium has extra mass. What we find is that if uranium splits, we go from an inefficient system of 7.5 MeV per nucleon to a more efficient system of 8.3 MeV per nucleon. And that doesn't seem like very much energy. What are we talking about? 0.8 million electron volts? It's really not a lot in terms of joules, but remember, that's for every nucleon. Let me finish this word so you don't think it's nucleus. That's for every nucleon, and inside of uranium, it's got 235 of them. So that leads us to 260 million electron volts for each nucleus of uranium-235. And if you've got a pound of uranium-235, you want to guess, like, ballpark how much, sorry to use a pound as being colloquial with my United States people. What's up, US? I'm sorry, your system sucks. If you've got a kilogram of uranium-235 and you, well, you got a kilogram of uranium-235 and you're going to, what, just estimate how many atoms you've got? You've probably got, what, 10 to the 23rd, maybe 10 to the 25th, I don't know, you make the call, you could figure that out. 10 to the 28th, what do you think, 10 to the 27th? You've got an enormous number, and if you multiply that by this, then you'll find that you're talking about some significant energy here. So, we could do a lot of things with that, but let's first understand how this happens. What we actually end up doing is you, and Hahn and Strassmann kind of opened the door for this, you take uranium-235, and you hit it with a neutron, actually. Neutrons, how many protons are in a neutron? None. What nuclear? Yeah, there we go. So I'm adding these two guys together, and that happens, well, if you get it just right, that neutron will be absorbed by the uranium-235, and it will become, you guessed it, uranium-236. Oh, I always want to make a fraction here. It's such a terrible habit. 92 uranium. The problem is it's not just regular uranium, it's actually asterisk excited nucleus uranium. So what we're doing is we're giving it some energy and an extra neutron, and it's so far apart that it actually wants to split apart. What could happen then is that the uranium asterisk 236, 92 could then fracture into what? Barium 141? Okay, barium is 56 on the periodic table, and you could get barium and something else. And I'm going to leave that as a problem for you. What the heck would come out if barium came out one side? I want you to think of this picture here. You've got an atom that's fracturing into barium here and something on the other side. And you can bet that something's going to be conserved. You figure out what things are conserved and tell me what you can know about this element over here. But the other thing you get, well, you're going to get a neutron. And you're going to get a neutron. And you're going to get neutron. So let's sit back and think for a minute. Imagine you've got some uranium-235 and you fire a single neutron in it. Guess what? When that uranium-235 becomes uranium-236 with an excited nucleus, it may then decay into these two products, which don't really do anything interesting, these daughter particles, and 3 neutrons. Let me put a purple circle around these guys and wonder about them. What do you think these neutrons will then do in your enormous sea of uranium-235? What do you think? Well, let's draw some uranium-235. I'll set up some uranium-235 for you, and you can kind of imagine what's happening. Here's some uranium-235. Okay, and here's an incoming neutron. Here we go. And it hits this guy. Pew! This guy fractures into 3 neutrons. Wait, one goes this way, and one goes that way, and one goes that way, say, right? But this one just got hit with a neutron, so one's gonna go this way, one's gonna go that way, and one's gonna go that way. But this guy just got hit with a neutron, and one's gonna go that way, one that way, and one that way. But this guy got hit with a neutron, one's gonna go that way, one that way, and one that way. Meanwhile, that's sort of everywhere. This kind of looks like an atomic bomb. You'd better not do this unless you know what you're doing. This is called supercritical. Now, what you wanna do is you wanna have some carbon control rods or maybe something else that you can put up here that will absorb the neutrons, absorb the extra neutrons, so that on average, when one neutron comes in, we can cut off 2 of these pathways and just have 1 neutron go out. So we have a steady stream of neutrons flowing through and getting our uranium-235 to uranium-236. But not in a dramatic way. We want it to just be critical. If we kill 2/3 of the pathways, then we can have it going nice and steady. So inside of your power plant, you probably want to have some control rods that you can control how fast the reaction is going so you don't melt down. That is, in theory, what Homer Simpson is supposed to be doing instead of eating donuts. So, uranium-235, interesting question. There's a lot of it inside of Earth. The reason it's there is because it's left over from supernovae, and the Earth formed from a gas in space that had uranium-235 in the gas, and it just condensed and was stored, thankfully, a good bit of it was stored in our crust. So you can dig it up. Uranium-235 has a reasonably long half-life, but you need to purify it because uranium-238 is just going to get in your way. So if you want to make a bomb, then you do all that stuff. If you want to make power, then you want to cut off these 2 pathways with some control rods in a reactive kind of system. Okie dokie, that is it for fission. Did I say fission? Yeah, fission. Fission. You been fishing today? Okay. Check this out. I'm going to give you a little bit of a primer on fusion. Fusion is an excellent technology because all you need for fusion is a whole bunch of hydrogen. Hydrogen, I mean, that's a proton, right? Awesome. You need oh, and some electron, right? Whatever. I don't really care about that. I'm saying if you have hydrogen and another hydrogen, look at this graph right here. Where's my graph? Look at this graph. You can get energy by going from here to here. That's a small amount of energy. Where was our energy? That amount right there. But if you go from hydrogen to helium, that's an enormous amount of energy per unit mass. Holy cow! Wait, question for you. Where is hydrogen? Why isn't hydrogen on this graph? Can you tell me why hydrogen's binding energy per nucleon is not on this graph? That's a little puzzle for you to figure out. But if you have deuterium, and deuterium is naturally occurring in seawater, you could just filter it out, preferentially get the deuterium together, and then you could have a fusion reactor. To fuse means to bring things together. And if you are fusing things together, then you'll get yourselves, well, you'll get yourselves an enormous amount of energy. The problem is there's this huge energy barrier that you have to overcome. Why is the energy barrier present for fusion? I guess because if I push this guy that way and this guy that way, they'll stop going eventually, unless I keep pushing. Turns out that the temperature needed for right here is super hot. If the temperature is high enough, then some of these protons will end up getting past their electrostatic repulsion and into a nuclear force. I guess, what do you have to get them? Within 10 to the minus 15th meters, that's a Fermi, right? If you get within 1 Fermi of each other, then they will suddenly spontaneously be attracted. Wow, it's like they don't like each other until you get them so close. It's like, is this like the Breakfast Club? I kind of think it might be. Okay, but the protons don't like each other, and that's why fusion has to be incredibly hot. There are technical difficulties. You're trying to set up a fusion reactor. You're probably thinking, ow, it's melting through everything that I put it in. That's kind of annoying. You make a fusion reaction inside of a cup right here, and the bottom of the cup is gone. And then the fusion reaction is down here, and it's melting through the table, and then it's melting through the floor, and, well, you just drop some fusion reaction into the middle of the earth. That's kind of annoying. You could plasma contain it. You could put it in a magnetic field. Anyway, nobody has quite surmounted these barriers. It's really expensive to plasma contain something because you need strong magnetic fields if you're doing it in a significant mass. And these problems are still remaining. If you are interested, you might look up something called cold fusion. We don't really think it can happen, but if it could, it would change the world. Tell you what, you figure out cold fusion, call me. We'll talk. Before you call anyone else, please call me. Now let's talk about some interesting things with radiation. First of all, I want to tell you that radiation has enormous amounts of energy. We're talking about alpha particles, beta particles, gamma rays, or even if you're talking about fission or fusion, we're talking about millions of electron volts. And these suckers can cause electronic transitions, which can rearrange molecules. In fact, these guys can rearrange thousands of molecules. Rearrange thousands of base pairs of your DNA. And that means that you will not be the same if you get hit with some radiation. In fact, most of these mutations that happen in your base pairs of your DNA from radiation will just kill the cell. Oh shoot. Oh, some of them turn off the instructions that regulate the cell and the cell starts reproducing like crazy. And then you've got cancer. That sucks, right? Stay away from radiation. But the fact that radiation kills cells can actually be useful. Sometimes they just take a radioactive source and set it on top of the cancer. Then the cancer all the cells will die, right? Oh, the base pairs will get so screwed up. So that's fun. Also, you could use radiation for something called positron emission tomography. That's a pretty cool idea. What if you had some fluorine-18? That's what I'm talking about. You'd need nuclear, what would you need? A particle accelerator down the basement of your hospital? Yeah, but you get the fluorine-18. It's got a half-life in terms of hours, so you have to make it on site right there, and then you get it turning into oxygen, and a positron comes out. Oh, funky. And an electron neutrino. Now that's a real neutrino going forward in time, but this is an electron going back in time. So that's kind of interesting. But the cool thing is when this positron is emitted in your head, see, you've put this fluorine into your bloodstream, and it's pumped up into your brain, and the electron will actually annihilate part of your brain. Just a little bit. It destroys part of your brain because it actually causes an electron in your brain to stop existing, as it also stops existing. And because they're antiparticles for each other, they cancel each other out, and, well, 2 gamma rays come out. You get, well, if you take an electron and you take a positron, then that's going to go to a gamma ray going this way and a gamma ray going that way. And if you've got a detector out on the outside of your head, you can see the light coming out this way and see the light coming out that way, and you can figure out where it came from. Cool thing about it is you can actually figure out what the person's thinking about based on where the fluorine-18 has gone in their head. So PET scans are really cool. Also, you could do MRIs. And MRIs use the fact that inside the nucleus, well, the nucleus itself is actually a magnet. So you can line up nuclei with a magnet and then knock them down and then watch how they spin back up again. Anyway, my argument is that you should keep studying physics. Doc out. So if I have, for instance, a proton here and another proton here, they could reduce their energy if they were in fact bound by the strong nuclear force. So the mass of one proton and the mass of one neutron, for instance, or the mass of proton and proton as I've drawn here, the masses of them separately is more than the mass of them in a nucleus. Like let's take one of those and one of those and one of those and one of those. We got a neutron here and a neutron here, and we've got a proton here and a proton here. If I add up the masses of all of these things, it's significantly more than if I make myself a helium nucleus. Something N equals A, B, what? All right, you look that up, figure it out. Watch this. I've got these numbers. There's one important number here, which is the top, 8.8 MeV. That's millions of electron volts. And then if I go up here, what the heck? Okay, great. And then it jiggles around a little bit and ultimately peaks right there at 8.8 million electron volts, and then it gradually goes down. This process here is rather slow, so slow that if I nucleus. So I'm going to make you a graph, in fact, of the binding energy per nucleon, and that graph looks like this. Here's a good graph. We've got an axis here, which is binding energy per nucleon. Okay, and then over here, we've got mass number. So as I'm talking about bigger and bigger elements, I'm going to be going this direction. What do we use for mass number? N, M, A, what? Oh, I think it's A. Okay, then, oh, what did we have? We had A plus, call out the next data point that I can see here. This is an interesting number to me. This data point right here is actually at 7.5 MeV. Okay, and what I really mean is this is the energy that binds the nucleons, so this ought to be negative. This whole graph, it always pisses me off to see it like this, but the whole graph ought to be negative. So the safest, the most bound things are right here at the peak, and the things that are least bound, most able to escape, are over here and like way over here. Wow, 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 way able to escape. So it turns out that psychology is wrong. There's this concept, they tell me, of Gestalt, and it means that you're more than the sum of your parts. I don't mean to hurt your feelings, but technically, physically speaking, you are less than the sum of your parts. What I mean by this is that, you know, that, well, what did they tell you? That mass is energy? Yeah, something like that. What I mean is, when, you know, nature hates change, right? You know, nature seeks to reduce energy. This is my last video. Sorry I'm throwing all this stuff at you. But what I'm saying is that nature seeks to reduce the energy of a system all the time. And lower energy actually means lower mass.